right, students, I'm going to continue our discussion of gravitational potential, and I'm going to introduce to you sort of formally the idea of an equipotential surface. We're going to talk about potential gradient, gravitational fields, the relationship between those two, and then we'll talk about finally about the escape velocity, which is the velocity needed by an object to completely escape the gravitational field of a celestial body. Okay, so the first thing I want to talk about is something called an equipotential surface. Now remember that gravitational field lines point inwards towards the center of a mass. Any mass placed at a point P experiences a force pulling it as shown towards the center of that mass, okay? And the distance r makes a big difference, and obviously the mass of that object at point P also makes a difference. Now, around every mass, capital M, which of course is the mass of the thing creating the field, at a certain r, okay, we have something called the gravitational potential, which I described in the last video as being the ratio of the gravitational potential energy per unit mass, okay, which is negative gm over r at a certain r. It's the amount of energy per unit mass that an object placed at the distance r from the center requires by being in that gravitational force field. It has nothing to do with the mass of the object being placed there. So the gravitational potential V sub g at point P depends only on the mass of the object creating the field and the distance between the point P and the center of that object, okay? All right, now we talked a little bit in class about topographic maps, okay? Equipotential surfaces are essentially topographic maps of gravitational potential, okay? In the case of a topographic map, where we are basically projecting a three-dimensional image on a two-dimensional surface, and we have lines called lines of equal elevation, and what they are is they're projected upon a flat surface, which is the map. Okay, the contour interval, which is the distance, the vertical distance between the different elevations, can vary depending on the map. Okay, the closer the lines are together on a map, the steeper the gradient. And sometimes topographic maps are shaded to make them more realistic. So, for example, if I were going to hike from this lake up to the summit of, looks like Mount Julius Caesar here, okay, what I would do as a mountain climber is I would avoid this spot right here because it's super steep and there's probably cliffs there. So what I would do is I would follow as many flatter areas as possible. I would probably go up here to this small lake, and I would probably ascend this ridge right here. I might even go over here to this pass and then ascend this ridge. There's lots of different ways you can go up. And so mountaineers and hikers need to be skilled at reading topographic maps and recognizing where things are steep, where things cliff out, and where things are flat, and where might be a good spot to pitch a tent and so forth, okay? So you really want to study this diagram right here as being two hills seen from the side and the elevation or topo lines marked there. Why am I spending so much time on this? Well, because it's exactly the same idea of lines of what are called equipotential, okay? So if you have a planet, mass m, okay, remember V sub g depends on r inversely. We can actually draw a line connecting all the points around that mass big M with the same gravitational potential. It's essentially a topographic map of what are called equipotential surfaces. Such a spherical shell, if you want to consider this as being concentric spherical shells around the planet, because everything's in 3D, this is called an equipotential surface. And equipotential lines are always at right angles to field lines, which is why it's very easy to draw them. And given the equipotential lines, you can always draw the field lines or vice versa, okay? All right? So equipotential lines for two unequal masses might look like this. If I were to draw the field lines here, okay, remember, because they're always at right angles, okay, the field lines would look something like that, right? Always at right angles like that, okay? And of course, the field lines would be pointed inward towards the surface, right? Or towards the center of this planet, okay? They would also go something like that. Okay. Anyway, you get the idea, and we'll do a little more practice on that in class, okay? All right, so let's try our first example. The diagram shows equipotential surfaces near a certain non-spherical body, okay? Calculate the potential energy of a 0.1 kilogram mass at P, Q, and R, okay? Well, pretty simple. So at P, my GPE is 300 300 joules. That's its mass times the gravitational potential, okay? And I guess that should really be a negative, okay? At Q, it's negative 250, and at R, it's also negative 250. Well, Q and R are on the same equipotential surface. So imagine what you can, the way to picture this body, which looks kind of like a potato, okay, is each of these are 1, 2, 3 different spherical shells that are kind of lopsided and shaped like potatoes themselves, and they're all centered around the body, okay? So the work that must be done on M to move it from P to Q is just the change in gravitational potential times that mass, okay? And that's 50 joules. From Q to R, I got 0 joules, of course, because they're on the same gravitational potential surface, okay? Or equipotential surface, okay? It's exactly the same kind of question. Part E is exactly the same kind of question is if you and your friend are hiking and you guys are at the same elevation on opposite sides of a valley, how much work would you have to do in your backpack to get over to your friend? Well, 0, because your friend is at the same elevation as you. You guys are on the same topo line or equi-elevational surface, if you want to think of it that way. Okay. All right. This potential gradient. Okay. I've talked about what makes a topo map, what makes a surface steep or when it's cliffy in the mountains. It's when the two topo lines are closer together. Okay. If I consider two equipotential surfaces a distance delta r apart with a change in potential between them of delta v, and if I move mass m from one equipotential to the other, the work to do this is m delta v. Well, that's also force through a distance, and that's mg times delta r. So assuming the 2 points are close together and g is about the same, then the gravitational field strength is delta v over delta r. As a derivative, this is dv over dr, okay, where v is a function of r, okay, because that's the gravitational potential, okay, d by dr of v sub v of r. The slope of the graph of v of r against r equals the magnitude of the gravitational field strength. The magnitude of the gravitational field strength is also equal to the acceleration due to gravity. Remember, they have the same units, newtons per kilogram and meters per second squared. G of r is itself then a function. Okay, very interesting. It's called the potential gradient. And we're going to do an example related to this right now. Okay, so this graph shows the variation with distance r from the center of a planet. Okay, use the graph to determine the magnitude of the gravitational field strength at the surface of the planet and at a distance of 3 times 10 to the 7 meters from the center. Okay, well, this is easy. For the first one, you need to figure out the slope of the tangent line at the surface of the planet, which I got to be what? About negative 3.8, 3.9, something like that, okay? And remember, I can get rid of that negative because this is delta v over delta r, which is really the gradient. It's the rise over the run, and I get 7.6 meters per second squared, or 7.6 newtons per kilogram. Up here, the slope is less. I got 0.2 newtons per kilogram. Now, very important to point this out, and you're going to need to be able to do this, okay? Given the function v of r, which is negative gm over r, you should be able to take its derivative and determine exactly what the slope is at any particular given point of r. Okay, I'll say that again. Given v sub r, okay, or v of r, which is a function which is negative gm over r, okay, you should be able to take the derivative of that and evaluate it at any particular point to determine the slope of the tangent line at any given radius. And what that actually gives you is the gravitational field strength at any given radius. In other words, it will tell you the acceleration due to gravity at any given radius. And you need to be able to do that without even seeing a graph, okay? Knowing the function. And remember the rules of derivatives that we studied before, okay? So this is a higher level topic, and I expect you guys to be able to use calculus to solve basic problems like this. And we'll practice in class as well, okay? Great application of calculus to physics. Okay. All right. Escape velocity is the minimum speed or velocity a body must have on the surface of the planet in order to completely escape the gravitational attraction. Okay. Or to get an infinite distance away. Or in other words, get from a distance of r naught being the radius of the planet, to a distance infinity away. Now, the kinetic energy lost by the mass moving to infinity is equal to 1/2 mv squared, because when it gets to infinity, its velocity is 0. Okay. The mass has just stopped. So the potential energy gain in moving to infinity equals gmm over r, of course, okay? All right, and by conservation of energy, since the change in kinetic equals the change in potential, we have that 1/2 mv squared equals gmm over r, and if I solve this for v, I get this expression for my escape velocity. That's the same expression that we got before, okay? And notice again that there is no mass term, and there's this funky factor of 2. Where does that come from? It comes from the 1/2 in the kinetic energy equation. Really cool stuff. So you see, you should be getting the sense in this topic that a lot of things we've studied previously, we're coming full circle, and we're kind of filling in the blanks and creating a gigantic puzzle and coming back to where we started while deriving the same things in a slightly different and more advanced manner, which is what we should be doing in a higher level, okay? Now, most things that are sent into space are designed to orbit the Earth. So they're launched at a speed which is less than the escape velocity. If they were launched at a higher speed, they would not even orbit the Earth, and they would fly off into outer space, okay? So as a very basic example, let's go ahead and find the escape velocity of the Earth given the mass of the Earth and the radius of the Earth. Okay, I got that it's about 11.2 kilometers per second. That's pretty fast. Okay, how about the radius of a star of mass m? What must the radius of a star of mass m be such that the escape velocity from the star is equal to the speed of light? That's an interesting question. Well, very simple. You use the same expression for the escape velocity, but you set v equals to c, where c is the speed of light, which is 3 times 10 to the 8 meters per second. We haven't studied the speed of light very much yet. Okay, all right. Then when you solve for r, you get that r is 2gm over c squared. Okay. Now what's cool about this, and we'll study this later when we talk about astrophysics and black holes, is that if a radius of a star is equal to or less than this, nothing can escape. Not even and it's called a black hole. And this radius has a name. It's called the Schwarzschild radius of the star. Pretty cool stuff. Okay. And we could actually work out the numbers if we were given the mass of a star. Okay, in this particular case. And in fact, let's do that considering the mass of the sun. Very, very interesting discussion following here, okay? So we have that r is 2gm over c squared. Great. Now, the mass of our sun is 1.99 times 10 to the 30 kilograms, okay? The mass of a neutron star, it turns out that a neutron star is the evolutionary stellar step just before a black hole. So if a star becomes a black hole, it was a neutron star at one point before that, okay? Turns out that neutron stars have masses that are approximately equal to the mass of our sun, but they have radii that are about 10,000 meters. Holy moly, about 10 kilometers. That's a lot of mass in a small space, and it turns out that when you have that much mass in a small space, that it's that dense, that it has such a gravitational field that even photons cannot escape. Okay, so think about this. For the sun, then the necessary radius to capture light would be, putting in the mass of the sun into this equation which I derived before, it would be about 3 kilometers, okay? And in fact, neutron stars do collapse into black holes, and the typical neutron star, here's a picture of a neutron star if it were on top of New York City. Here's Long Island and Manhattan. You can see that neutron stars are not very big. So again, just to blow your mind, in this sphere would be the mass of our sun, and it would be less than the size of the metro New York area. Holy moly. Interesting stuff.